Hello everybody and welcome to this video on section 7.8, which you are watching due to the snow. Let me say up front that I had meant to make a more high-tech video than just looking at this PDF document like we do in class. I was going to make slides with some more in-depth examples on them, etc. But when my school is canceled, my kids' school is also canceled, which means that I have to find time in between keeping them entertained to make a more fancy video, and I was just unable to find that time. So anyway, hopefully this is of use to you. I'll talk over this like we do in class, probably more briefly since we won't be interacting. So section 7.8, the goal of the section is to establish a connection between the concepts normal subgroups, quotient groups, homomorphisms, as we had back in the ring context. So back with rings, we also had a connection between these concepts, and the connection was this. Given rings R and S, a homomorphism from phi from R to S, the kernel of phi is an ideal, and recall an ideal is like the analog of a normal subgroup, so the kernel was an ideal, and when you did R and modded out by the kernel and formed that quotient ring, you got a ring that was isomorphic to whatever phi was hitting over an S. This is a subring of S over here. That could be S, if that phi map is onto. Anyway, so the kernel is what linked these concepts back for rings. The concepts of quotient ring, homomorphism, and ideal. Sorry, that's what that should say. There should be an ideal in there. But anyway, so we've seen this before, right? We've seen a connection between the idea of a quotient ring, a homomorphism, and an ideal, and it was this. This was the first isomorphism theorem for rings. So that was All's theorem 6.13, the first isomorphism theorem. So we're going to do the same thing for groups. Okay, so like many of these group theory sections, even though groups are not the same as rings, you can develop the exact same concepts. And, it's not like the concepts match exactly. So an ideal, for example, the definition of ideal is quite a bit different from the definition of normal subgroup. But normal subgroups play the same role as an ideal. So once you get sort of the right vocabulary in place, you can develop the same kind of theorems and theories for groups that you did for rings. Okay, so with all that in mind, here's the section. First definition is to define the kernel. This was a concept and a term from ring theory that we defined back then, so we have to redefine it here in terms of groups because we're in a new context now. So if you have a map from G to H where those are groups, the kernel is the set of little g and big G that get mapped to the identity in H. So it's a subset of G. Okay, the kernel of phi is a subset of G. Which subset? Well, it's the set of things that get crushed to the identity, basically. Okay, so here are 4 questions about what a kernel is for a given map. So let's just go through these one at a time. So first of all, if you map Z16 to itself, and what you do is you stretch things by 4. So like 1 goes to 4, 2 goes to 8, 3 goes to 12, etc. You can ask, what's the kernel of that? Well, to answer that question, first of all, you have to know what is the identity element of the range. And in this case, Z16, we're assuming addition is the operation. Therefore, the identity element of Z16 is 0. So now you're asking yourself, okay, the kernel of this map, it's the set of things that get mapped to 0. So notice phi of 0 is 0. Phi of 2 is 8, which is not 0. Phi of 3 is 12, which is not 0. Phi of 4 is 4 times 4 is 16, which is 0. So 4 is in the kernel. 0 is in the kernel, 4 is in the kernel. And you can check the rest, but it turns out that 8 and 12 are also in the kernel. So the kernel of that map is the set 0, 4, 8, 12, which, not coincidentally, is a subgroup, right? Multiples of 4, that's a subgroup of Z16. Okay, this next map, mapping Z16 to Z8, just to be clear about what I mean here, all I mean is take your element of Z16 and now think of it as an element of Z8. So like 5 maps to 5, because when you think of 5 as an element here, you could also think of it as an element there. Something like 9, like where would 9 go? Well, if you want to think of 9 as living in Z8 rather than Z16, you're talking about 1. So this map will send 9 to 1, it will send 10 to 2, etc. So why don't you just pause this video now and think about this question. What's the kernel of that map? Okay, assuming you've paused the video and now have come back, the kernel you should have gotten is 0 and 8. That's the subset of Z16 that will map to 0 here. 0, thought of as an element of Z16, is still 0 here. 8, thought of as an element of Z16, is not 0, but when you think of 8 as living in Z8, it now is 0. Okay, so once again, notice we get a kernel that's a subgroup, right? The set consisting of 0 and 8 and Z16, that's a subgroup. Okay, next question. G is a group. Map from G to G that just sends a little g to itself, right? Everything gets left alone. What's the kernel of that? Okay, so you have to, again, pause the video, maybe think about that for a minute or two. Okay, assuming you're now back, we have to think about the set of things in G that gets mapped to the identity in G. Well, the only thing that's going to get mapped to the identity in G is the identity already. So if G is not the identity, then G doesn't get mapped to the identity, So the only thing that gets mapped to the identity is the identity. So here the kernel is just a single element, consists of a single element, just the identity of G. Finally, let G be a group. Map from G to G defined by phi of G is E. What's the kernel of that? So the kernel is the set of things that get mapped to the identity, and here we are forcing everything to get mapped to the identity. So this question 4 is the opposite extreme of question 3. Okay, so here everything in G maps to the identity, so the kernel is everything. The kernel is G. So hopefully these questions have gotten your feet wet with what a kernel is. I mean, again, you've already seen this concept before, it's just now we've had to recast it for groups. So here's our first theorem about homomorphisms and kernels. Let phi be a map from G to H, kernel K. Then K is not only a subgroup, which we had some suspicion of before, right? Turns out it's a normal subgroup. Okay, so if you want to show something is a normal subgroup, you first must show it's a subgroup, then show it's normal. Okay, so we'll show subgroup first. Let's let A and B be a couple guys in the kernel. Then notice phi of AB equals phi A, phi B, which equals EE, which is E. Okay, so phi, when applied to AB, gives you the identity. Thus, by definition, AB is in K. So K is closed under multiplication. Next, let's show it's closed under taking inverses. Note, phi of A inverse equals phi of A inverse. You can put the inverse on the outside. So here, this A inverse is happening in G, then you are mapping that over. Here, you are mapping over first. So phi of A is an element of H, then you are inverting that, okay? But notice, right, phi of A, well, A was in the kernel, right? I chose A to be in the kernel right there. So phi of A, we know what that is. It's just the identity. And the identity inverse is just the identity, okay? So if A is in the kernel, then A inverse also gets mapped to the identity, meaning A inverse is in the kernel also. So K is a subgroup. To show it's normal, it suffices to show this. GA, G inverse is in K for all G and G. So this is a theorem from last time or the time before. Okay, but anyway, so this is just plugging into a previous theorem. If you ever want to show a subgroup is normal, you can just show that given an element of the kernel A was arbitrary, as long as GA, G inverse is still in the kernel for anything in G, then the subgroup is normal. So let's let G be in G. Then notice phi of this element, GA, G inverse, we can split phi over the product. And then phi of A is the identity. And look what you have here, phi of G inverse. So those guys cancel each other out, and you're left with the identity. Therefore, for any G and any little a in the kernel, GAG inverse is in the kernel. So the kernel is not just a subgroup, it's a normal subgroup. So from last time, we know when you're dealing with normal subgroups, you can form a quotient group. Therefore, G mod the kernel is a thing, right? G mod the kernel is a group unto itself, and you could, of course, ask what that group is, and that's basically what the rest of the section is about. Okay, so here's another theorem that should look familiar from the ring context. Let phi G to H be a homomorphism, kernel K. Then the kernel is trivial, consists of just the identity, if and only if phi is 1 to 1. So I'll let you think about that, but the proof, we've seen this before. We proved this theorem for rings. The logic translates for groups. I mean, here's a little sketch, right? Phi of A equals phi B, if and only if phi of A, phi B inverse is the identity, if and only if phi of A, B inverse is the identity, if and only if A, B inverse is in K, right? So if A, B inverse is in K and K is trivial, then you get the A equals B. And everything here was if and only if, so you can unwind it. Anyway, so back in ring land, right, kernels were ideals. Here in group land, kernels are normal subgroups, so that analog holds. Back in ring land, your map was 1 to 1 if and only if your kernel consisted of just the identity, and that's still true here. So those theorems translate through. Okay, here are a couple other theorems that I won't prove for you due to time constraints. If n is normal in G, then this map defined by little a goes to its congruence class. So this map from G to the quotient group, where you send a little group element to its congruence class or its coset, that's an onto homomorphism with kernel n. Okay. So basically, any normal subgroup is the kernel of some map, is what this is saying, right? So since n is normal, you can form the group G mod n, right? And then there's a map from G to G mod n defined this way, whose kernel is n. Okay, so all normal subgroups are also kernels of a map, right? So you can start to see how kernel sort of unifies the concepts of normal subgroups and quotient groups and homomorphisms. Okay, so here's another theorem. It's the first isomorphism theorem, just recast for groups. We said this for rings. It's still true for groups. Let phi be a map from G to H with kernel K. G mod K is isomorphic to the image of phi, just like it was for rings. So back up here for rings, where was it? Theorem 6.13, first isomorphism theorem for rings, said this. R mod the kernel, which was an ideal back then, R mod the kernel is isomorphic to the image. Same thing is true here. G mod the kernel, isomorphic to the image. This is just a group theoretic statement now, right? These are isomorphic as groups because we're in the group context. Okay, but the theorem is the same, so that's nice. So let's see an example of this being used. Okay, so let's let C star be the multiplicative group of non-zero complexes. Okay, multiplicative group. So we're thinking of the complexes under multiplication here. So let's let n be the subset of complex numbers with absolute value 1. So if you're not comfortable with that, because you're not comfortable with complexes, let me just say that the complexes form a complex plane, And I think all of you are familiar with that concept. So any complex number lives in the complex plane. The subset n here, that's the unit circle, is all I'm saying. So you got the plane in front of you, right? Look at the circle of radius 1 centered at the origin. Those are the complex numbers I'm talking about. The set of complex numbers so that when you square the coordinates of it, the a and b values, you get 1. So what you should be picturing in your head is the complex plane, right? That's the group. And then the subset of it that we care about is the unit circle inside that plane. Okay, so let me define a function phi from that group, C star. From that to R star star, where the notation here is cumbersome, but this is what your book does. R star star is the multiplicative group of positive reals, and the map is going to be defined this way. Send a complex number to the square of its first coordinate plus the square of its second coordinate. So first question, what's the kernel of that map? Well, you have to ask yourself, what's the identity in the range? R star star is the multiplicative group of positive reals. Therefore, the identity is 1. Okay, so you're asking yourself, oh, under this map, what gets sent to 1? Well, you can see from this definition of n what the answer is, right? N is the set of complexes, so that when you add the squares of the coordinates, you get 1. So by construction of this map, basically, right, the kernel is this subset n. Okay, so now we can ask, well, what group is C star mod that kernel? And it's actually not hard to see that this map, this phi map, it's not hard to see it's onto. So C star mod the kernel is isomorphic to the image, right? We know that by this theorem up here, 7.42. Well, what's the image? The image is everything. Okay, this is an onto map. So all that to say, this first isomorphism theorem, once you got a map going, you can start to see isomorphism relationships. So R star star, this multiplicative group of positive reals, that's a quotient group of C star. Right? R star star is isomorphic to some quotient of C star. Well, which quotient? Oh, the quotient where you build this map, and you mod out by the kernel of that map. That gives you R star star. So anyway, there's a nice little example of using that theorem 7.42. Okay, so if you let n be a normal subgroup of G, you can ask this question: what do the subgroups of G mod n look like, and what relationship do they have to subgroups of G? Seems like there should be some relationship, because the structure of G and G mod n, it stands to reason, have some relationship to each other, because G mod n is built from G. So anyway, there is a relationship, and the next isomorphism theorem gives it to us. This is the third isomorphism theorem for groups. So a couple of comments about that. There was also a third isomorphism theorem for rings. We just didn't cover it. It was in the homework that wasn't assigned. So there was a theorem like this for rings. We just didn't do it. The second comment to make is that there is, of course, a second isomorphism theorem for groups. If you want to see what it is, it's in the homework that's not assigned. But anyway, so there's no typo here. This really is the third isomorphism theorem. We didn't skip anything. Okay, it says this. Let K and N be normal subgroups of a group G such that K contains N. Okay, so N is living inside of K. Then it turns out K mod N is a normal subgroup of G mod N. And the quotient group G mod N, mod K mod N, is isomorphic to G mod K. Okay, so that's a lot to say, right? But let's refine this a little bit, okay? So when you form G mod N, right, what are you doing? You're crushing all of N to the identity and accepting the consequences, right? That's what you're doing. So everything that was inside of N is now just crushed to the identity, right? K contains N. So K has a bunch of stuff that gets crushed to the identity, but it has some other stuff that doesn't get crushed to the identity. It has some survivors or something, right? So this K mod N, right, that's a normal subgroup of here, so it includes the identity, right? But so basically this set here consists of everything in K after it gets crushed to whatever it gets crushed to, So K, for example, contains the identity element of G, which does get crushed to the identity when you do this G mod N. But K has other stuff that doesn't get crushed to the identity. So anyway, what this set is, it's just the set of elements of K, many of which have been glued together because of the crushing action that's going on. But still, you get a set of cosets here, and that set turns out to be normal here. And so since this is normal in this, you can form a quotient group, You You can form quotients inside a quotient. All you need is normality to form a quotient. So you can do G mod n. Sorry, that was my phone. Anyway, you could do G mod n. That's the overgroup, right? Mod this normal subgroup. And notice what's happening here is, what's so nice about this theorem is saying that this sort of modding thing, which has nothing to do with actual fractions, right? This is just notation, the slash symbol, okay? G mod n is a group. You can then mod out K mod n, which is a subgroup. Has nothing to do with dividing fractions, right? But this theorem is saying that this behaves like fraction division. Because if you treat G, N, K, N as numbers, right, the n's just cancel, right? So like what? 1/3 divided by 5/3 is just 1/5, you know? So the third isomorphism theorem is saying that when you mod with mods, it works just like fraction division, which is shocking that that's true, you know? And that's really surprising and nice. So anyway, all that to say, if you start with something normal in G that contains n, right, and then you look at the corresponding subset in G mod n, K mod n, you're going to get a normal subgroup down there. Okay, so that's one thing to know about the subgroup structure of G mod n. The next thing to know is this: if n is normal in G and K is any subgroup of G that contains n, then K mod n is a subgroup of G mod n. Okay, so if K is a normal subgroup, right, that's what we had here. If K is a normal subgroup of G containing n, then K mod n is a normal subgroup down in the quotient. Okay, so K, though, might not be normal. Who knows, right? But normal or not, you at least get a subgroup when you look at the version of K that like occurs after you've crushed n to the identity. So any subgroup of n corresponds to a subgroup down below in G mod n. Furthermore, if T is a subgroup of, G mod n, should say there, right? Then there exists a subgroup H of G such that H contains n, where T is the version of that H. Okay, so given a subgroup below, given a subgroup in, G mod n, right? Given a subgroup down here, there's some other subgroup back in the original group G. That other subgroup contains n, and T is just the version of that subgroup, right? So there's a correspondence between subgroups of G containing n. Right, subgroups of G containing n, there's a correspondence between those subgroups and subgroups of G mod n, is what this theorem is saying. Okay, furthermore, K mod n is normal in G mod n if and only if K was normal in G. So all that to say, right, the original question of this section is, what do subgroups of G mod n look like, and what relation do they have to subgroups of G? These theorems answer all of that, right? These theorems say that, oh, the answer is, if you have a subgroup down here, right, it's got a subgroup K, whatever, or T, right, you have a subgroup here, that subgroup came from a subgroup of G, right? Any subgroup down here came from a subgroup up here, and furthermore, that subgroup had to have contained n. So any subgroup of G that contains n gives you a subgroup in G mod n, right? And any subgroup of G mod n came from a subgroup back up top in G containing n. So just to use that, if G is Z20 and H is this subgroup, you can build the subgroups of G mod H using the theorems above. And so it'd be nice to have a board here, right? But what's going on here, if H is a subgroup generated by 10, in Z20 you're just talking about 0 and 10. This subgroup has only two elements, 0 and 10. The subgroups of G mod H come from subgroups of G containing 0, 10. So really this question just wants you to think about what are the subgroups of G that contain 0 and 10? And there are lots of them. Like for example, Z20 itself contains 0, 10, right? So Z20, the entire group, if you mod up by H, right, you're just getting G mod H, right? You're getting the big subgroup of G mod H, right? The entire group G mod H. There are, of course, other subgroups containing 0 and 10, like 0, 5, 10, 15, right? That's a subgroup containing this H. Also, 2, 4, 6, 8, 10, 12, 14, 16, 18. That subgroup also contains this. Okay, so basically this example, if we had a board, we could do it in full detail, right? Your book has an example with Z16 if you want to see your book. Anyway, sorry. Sorry, my kid just came in my room and is now staring at me. He's very interested in what I have to say. Anyway, so to do this example, you build all subgroups of G that contain H and then just crush them down to G mod H. And by the way, we know what G mod H is here. If you take Z20, hang on, buddy. You take Z20 and crush 10 to 0. Yes, buddy. Yeah, mom's coming to get you. If you crush 10 to 0, you get Z10, right? So every subgroup in Z20 that contains the subgroup 10, any such subgroup will then just translate to a subgroup of Z10. Okay, so anyway, this would be easier to see at a board, right? But again, your book has an example with Z16 that I would reference you to. And if you want to see this done in detail, we can do it on Wednesday. Okay, finally, the last concept from this section is the idea of a simple group. A group G is simple if its only normal subgroups are G and E. So every group has two normal subgroups, G and E, right? Every group has those. So you're not going to get around those, you know. If your only normal subgroups are G and E, then you are simple. Okay, so we're already running short on time here, but let me just say the idea of simplicity, it's not obvious from the definition. Yes, buddy. It's not obvious from the definition why that's important, but let me just say, like, one of the big projects of group theory in the 20th century was, given a number, a billion, a trillion, whatever, right? Given that number, what do the groups of that size look like? You know, what do the groups of size 1,000,000 look like? How many of them are there? What do their subgroups look like? Whatever, right? So basically, what I'm saying is people were trying to classify groups by size. Given a possible group size, can you tell me what those groups look like or not? You know, and it turns out that the answer is yes, but you really have to understand what the simple groups look like. And so we're not going to do much with this concept because we don't have much time left in the course, but the idea of a simple group lets people classify finite groups by their size, basically. So anyway, the idea of simplicity is core to that like big project of 20th century group theory. So just to get an idea of that definition, here's a first question: is D4 simple? And you can think about that if you want to, but you're asking yourself, right? Are there sort of non-trivial normal subgroups here? Are there normal subgroups besides that entire group and just the identity? And if you look back at your notes from, from the normal subgroup section, section 7.6 or something, you will see that the answer is no. D4 is not simple. We have seen multiple normal subgroups of D4. Okay, so for example, the set of rotations, that's a normal subgroup of D4. And so then in general, for a Dn, so not just a square, but like a hexagon or a pentagon or whatever, right? The set of rotations is always a normal subgroup. So the dihedral groups are never simple for any subscript there, okay? On the other hand, ZP is simple for any prime P, okay? And why is that, right? Well, ZP, it turns out, just doesn't really have that many subgroups at all, really, right? Because by Lagrange's theorem, right, any subgroup, the size of it has to divide the order of the group. So if your group has prime order, right, subgroups either must have size P, in which case you're talking about the entire group, or they have size 1, in which case you're talking about just a trivial subgroup. Okay? So anyway, we don't have that many groups going, right? But of the bag of examples we have, dihedral groups are not simple. Cyclic groups of prime order are simple. Okay, so that's the end of this section. Hopefully this was useful to you. Again, if you have any questions on any of this, feel free to ask on Wednesday. On Wednesday, we'll pick up with cryptography based on group theory. So we've done ring theory-based cryptography. So I wanted to show you what group theory-based cryptography looks like. It actually is quite a bit of a different flavor, even though a lot of our concepts between rings and groups have a similar flavor. Group cryptography is different. But anyway, so before we do that on Wednesday, be sure and ask me any questions you have on this material.